Hey class, Bob here. I'm going to describe the economic order quantity model. It's one of the first models in your inventory management chapter, chapter 10. Inventory is kind of this necessary evil. We need it to satisfy demand. We need inventory to, if we manufacture something, we need component parts to manufacture finished products. If we sell products, we need to have something on the store shelves. We need to have cars on the lot in order to sell our product. So it's this evil because it costs us a lot of money. If you ever drive by Bob Howard Auto Mall, do a quick mental calculation of how much money is on those car lots or are on those car lots. Um, Hundreds of cars, each worth tens of thousands perhaps, and you got millions and millions of dollars. That's millions of dollars in inventory that could be earning an income in some other way, or it's millions of dollars that someone's paying interest on. So inventory is awfully expensive, so we want to keep it to a minimum. In chapter 10 focuses on how do we balance that out? How do we keep enough inventory without um, without sacrificing um, a loss in opportunity? But we don't want to go overboard. So the first model in here is called the EOQ model, or the economic order quantity. And this, as the name implies, order quantity is an optimal amount to order. So we want to look at some relationships that exist and then kind of pinpoint a model for doing that. Okay, so if I wanted to, I could go to Sam's just once a year and I could stock up on um, Diet Dr. Pepper, let's say. And I drink a lot of Diet Dr. Pepper. So let's say I buy 1,000 bottles on January 1 and then I use them up throughout the entire year. Well, I'd only have to go to Sam's one time. However, I'd have a huge average inventory. On average, I'd have 500 bottles of pop lying around. So if you're wondering where 500 came from, my average inventory would be half of the order amount. I'd start the year out with 1,000. I'd end the year with 0. On average, I'd have about 500. So average inventory is going to be half of the amount we order. Now, if I didn't want to keep all that around the house, I could go to Sam's more frequently. Now, I'm going to have to order the pop more and more frequently, but my inventory is going to come way down. So maybe I go to Sam's once a month, and now instead of getting 1,000 bottles, I get less than 100. So my average inventory is something like 40, 48, 45, somewhere in there. Now, inventory went way down, but I'm having to make a trip to Sam's every month, so my orders went way up. Well, ordering has a cost, as does holding on to inventory. So the EOQ model attempts to balance these two things. Now, on my vertical or y-axis, I'm going to put dollars. And on my horizontal axis, I'm going to put the quantity I order. Okay. Now, as I order more and more and more, my uh, my ordering cost goes down. The cost of ordering goes down. Bigger orders mean fewer orders. So I'm going to introduce some things. Let's introduce a capital D, and that's going to be my annual demand. Okay. We're going to let Q equal the quantity I order. Okay. And if you look at two different types of cost, whoops, my marker quit working. Let's try it again. There we go. I'm going to have an ordering cost, the cost associated with placing an order. This could include inspecting the order once it arrives, could include shopping around, but there's a cost associated with procuring some type of a product we're going to sell. So this is ordering cost. And there's also a cost for holding on to an item. So that's the holding cost, CH. So depending on the item, the holding cost for an automobile is more than the holding cost for, say, a can of beans. But holding cost incorporates opportunity costs. So if we have an automobile sit on a parking lot for a year, that automobile is a $20,000 car, and we're paying 6% interest to own that, then the holding cost would incorporate that interest. It might also incorporate the fact that we've got to pay a security guard to keep an eye on those cars at night. Or if our holding cost belongs in a warehouse, those holding costs include those warehousing overhead type costs, heating and cooling and security, etc. So whatever it costs us to hold on to inventory, we express it as CH, and that's typically a per unit per year number. Okay, the holding cost per unit per year. Per unit per year. Similarly, the ordering cost is per order. That's probably common sense. Don't need to write that, but I will. Okay, so every time I place an order, I incur some type of an ordering cost. Okay, so we've got some variables here defined here. Now, as the quantity goes up, the holding cost goes up. So let's talk about my holding cost. My holding cost is going to be my average inventory times my holding cost per unit per year. So let's talk about that. Q over 2 times CH. Q over 2 is simply my average inventory. If I order in increments of 1,000, on average, I'm going to have 500 units laying around. Because what will happen, let's say this is the quantity I ordered, this is the amount of inventory I have on hand over time. So let's say this is that 1,000 units. I order 1,000 and I use that inventory up. And then when I get to 0, I order another 1,000 and then I use that inventory up. So inventory is going down, down, down. I get to 0. I receive another order of 1,000. I use it, use it, use it, use it, use it. And this repeats itself. And on average, I'll have right here 500 units. So average inventory, it's half the amount we order. Think about it. If you drink a glass of water, you start with the water being full. You start with, say, 16 ounces of water. You finish with the glass being empty, 0 ounces. On average, you had 8 ounces of water in that cup. So average inventory is half the amount we order. And so we use that in multiplying it by the cost per unit per year for holding on to inventory. So even though we order 1,000 units, we're only on average going to have 500 laying around the store. So we're gonna base that holding cost on that 500. Okay, I'm using 500, 1,000, just kind of pulling numbers out of the air. Nothing special about those numbers. Now the opposite thing is that when I raise the quantity I order, the ordering cost goes down. Again, if I buy 1,000 bottles of pop at Sam's, then I don't have to go to Sam's as frequently as if I just get about 100. So the bigger the quantity of the order, the lower my holding costs. So how many orders do I have to place in a particular year? Well, that's going to be my annual demand, how many I need in a year, divided by the quantity I choose to order. So if I need 100,000 units of a particular product I sell, and I order them in quantities of 10,000, 100,000 over 10,000, that means I've got to place 10 orders per year. So this D over Q represents the number of orders I place in a year, and we're going to multiply that times the cost of an order. Okay? So D over Q is the number of orders. C O is the cost of placing an order. Okay? If we were to add these two together, we'd have a curve that looked like this. And this is just nothing but this plus this equals this. This plus this equals this, and so on and so forth. That is just the total cost curve. So this top curve is total cost, and it equals to my average inventory times the holding cost. That's my annual holding cost right there, Q over 2 times C over H, plus the number of orders I place times the cost of ordering. Okay, so there's my total cost, which is just the sum of these other two costs. Now, if I do that, it's going to come right through here at the minimum point. Pretend you drop a marble in this top curve. That marble is going to come to rest in the middle there, and it'll come to rest where the slope of that line is 0. Now, you don't have to do this, but if you take the derivative of the total cost curve, set it equal to 0 because the derivative gives us a slope, and you solve for Q, you get something called the EOQ, the economic order quantity. And that's this quantity over here, this quantity that minimizes, that finds the minimum, the lowest point of that total cost curve. That's this right here. It's 2 times D over holding cost, or 2D, let's see, that should be a 0. 2 times D times my ordering cost over my holding cost. I'm going to take the square root of that. Okay, that's a formula I'd provide for you on an exam, or you'd have available too. You don't need to memorize it, but it's 2 times D times the ordering cost divided by the holding cost, and then you take the square root of that, and that gives you the EOQ. Okay, so let's have an example. Let's say I have a particular product that I sell, and my annual demand is, let's say, 10,000 units. Let's say that the cost of ordering those units, every time I place an order for those products, it costs me $100. And let's say it costs me $2 per year per unit to hold on to those. So what would the optimal number of units to order be? Well, it would be 2 times 10,000 times 100 over 2, take the square root of that, and that's, what is that, 20,000, 2 million over 2, a million, the square root of a million. So let's pause and calculate that. Okay, and the square root of a million, I should have realized you can do that in your head. The square root of a million is just 1,000. So in this situation, we would order in quantities of 1,000 at a time. So my total cost would be my average inventory, 1,000 divided by 2. So on average, I'm going to have 500 of these laying around, and it's going to cost me $2 for each of those. So my annual inventory costs are going to be $1,000. Okay, my average holding costs are going to be $1,000, and then I'm going to spend, when I place orders, I'm going to place 10 orders a year because I need 10,000 of these divided by 1,000. That's 10 orders a year at a cost of ordering each time of $100. So that's also going to be 1,000. 10 times 100 is 1,000. So my total costs are going to be $2,000. So that's this point right here. This is 2,000. This point right here is 1,000. Okay. Now you notice if I order more, if the quantity I ordered goes up, then I go up the total cost curve. If I order fewer than that, then I go up the total cost curve. So that is the optimal number to order. 1,000 is the optimal number to order in an effort to minimize the sum of my holding and ordering costs. And that is the total cost and EOQ models.